Assalamualaikum and good morning to my respectful panel. My name is Aini Binti Ijaman with metric number AN190124, and I would like to present on my final year project with the title of Fluorine-Free Superhydrophobic Silicone Rubber Surface for Self-Cleaning Properties via Deposition of Stearic Acid Modified Kaolin Nanoparticles. First of all, I would like to briefly explain on the abstract in my project. Recent development of the superhydrophobic surface via fluorine as nanoparticles for self-cleaning application is harmful to environment. This study is conducted to fabricate superhydrophobic surfaces that are simple, cost-effective, and environmentally friendly. Modifications of kaolin nanoparticles via stearic acid was employed to fabricate stearic acid modified kaolin nanoparticles onto the silicone rubber surface. Recent results prove that stearic acid successfully covered the nanoparticles and stearic acid kaolin modified was distributed onto the silicone membrane to show hydrophobicity. The results obtained from the self-cleaning properties have proven that the surface film showed better self-cleaning performance. However, results obtained do not show superhydrophobic outcomes for all the modified samples. Next, for the introduction of my project, I'm going to divide it into three parts, which are research background, problem statement, and objective. For my research background, in recent years, superhydrophobic surface application with self-cleaning properties had attracted a lot of interest. Taking lotus leaf, butterfly wings, water strider slates, and so on as inspiration from nature to fabricate superhydrophobic surface because water is seen to repel on many natural surfaces. By applying and elaborating this concept of lotus leaf in the field of superhydrophobicity on the surfaces, many researchers around the world highlighted the significance of surface chemistry in their research. Surface roughness together with low surface energy exhibited superhydrophobicity, where surface roughness improved behavior of hydrophobic surface, making water droplets become nearly spherical on the surface, while low surface energy tends to reduce surface wettability. Hence, it prevents addition of water onto the surface. In addition, problem statement of my project is the use of fluorine based in the manufacture of superhydrophobic surface have been widely developed for self-cleaning and anti-fouling properties. Roughness of the surface with combination of fluorine as nanoparticles that have lower surface energy are crucial parameters to form a superhydrophobic surface. However, fluorine is known to be harmful to the environment and human health, especially when it is released to the atmosphere. Therefore, this research has been done to improve and modify the superhydrophobic surface to make it free from fluorine and environmentally friendly. The use of stearic acid modified kaolin nanoparticles offers a lot of benefits, which is cheaper, low cost, accessible, and particularly environmentally friendly than fluorine. Other than that, kaolin is known as a type of clay that is very fine in size, which naturally can be found in nature without needing harmful and hazardous methods to extract it. Objectives of my studies are to fabricate superhydrophobic silicone rubber film via preparation of stearic acid modified kaolin nanoparticles, to characterize surface wettability and physical-chemical properties of the superhydrophobic silicone rubber film, and lastly, to evaluate the self-cleaning properties of the superhydrophobic silicone rubber film. In order to achieve my study, there are several methods that I followed. Firstly, the fabrication of superhydrophobic stearic acid modified kaolin nanoparticles silicone rubber film. As general, I prepared the stearic acid modified kaolin nanoparticles first, then followed by preparation of the silicone rubber film. So basically, I mix kaolin into the solution consists of 1 weight % ethanol to stearic acid. Then the mixture is stirred with selected temperature. To get stearic acid modified kaolin nanoparticle To get steady acid modified kaolin powder, the mixture is centrifuged and dried in an oven. The steady acid modified kaolin nanoparticles was controlled with different weights of dispersed kaolin, such as 0.2 gram, 0.3 gram, and 0.4 gram. The powder obtained is then mixed into the solution of preparing the silicone rubber film and stirred until it fully dissolves. After that, casting the solution by using casting knife film. The mixture was left temporarily on the glass slide, then finally was fabricated by drying in an oven for 2 to 3 hours with temperature of 50 degrees Celsius until the solvent was completely evaporated. The concentration of the steady acid modified kaolin nanoparticles added was differ at 5 weight%, 10 weight%, 50 weight%, and 20 weight%. Secondly, the method involved is the characterization of surface wettability and physical-chemical properties of superhydrophobic silicone rubber surface. The surface wettability of the sample was evaluated via contact angle by using the sessile drop method. Using the ionized water, the contact angle was measured via the use of a contact angle device. A droplet was dropped on the 3 random points on the sample surface. The average of the random points was calculated to obtain the contact angle values of each sample. The characterizations of surface wettability and physical-chemical properties of the superhydrophobic silicone rubber film were tested by using field emission scanning electron microscopy, which is FESM, to study surface morphological features of film and size of steady acid modified kaolin nanoparticles. AFM was used to characterize the surface wettability and physical-chemical properties of the superhydrophobic silicone rubber film. Last but not least, the evaluation of safety properties. Superhydrophobic steady acid modified kaolin nanoparticles silicone rubber film. To stimulate dust for safety properties, graphite powder was used. The surface sample was evenly sprinkled with graphite powder. The angle formed by the sample surface and the bottom of the petri dish was approximately 10 degrees. The sample's upper surface was then constantly dosed with water using the dropper while pictures were being taken. For the next part, I'm going to explain and discuss on the results obtained throughout the study. The first result is surface wettability via contact angle. The surface energy of the materials determines the strength of the liquid attraction. Thereby, contact angle analysis was carried out to characterize the surface wettability of the pristine membrane and the steady acid kaolin modified silicone rubber film with different concentration by subjecting water droplets onto the samples. Based on the figure attached, there is no significant difference in the wettability of each sample. All the samples form hydrophobicity with contact angle more than 90 degrees when fabricated with steady acid modified kaolin nanoparticles. Fabricating a surface with low surface energy materials, which is steady acid, introduced appropriate surface chemistry to the surface. It resulted in greater resistance to high surface tension of water from penetrating into the silicone rubber surface. Based on the table attached, all the fabricated film except for the pristine membrane does not achieve contact angle of 150 degrees. The highest total contact angle value is only 113.9 degrees with concentration of 15 weight%. It means that none of the above films achieve superhydrophobic surface as expected. It might due to the insufficient surface roughness of the surface film. Film with 15 weight% was chosen as the best surface with hydrophobicity since it exhibits the highest contact angle among other concentrations. Although it does not achieve 150 degrees, the film proved that fabrication of steady acid modified kaolin nanoparticles in hydrophobic surface induced low surface wettability. Next, results shown is surface morphology analysis via field emission scanning electron microscopy (FESM). Image shown on the left side is the surface morphology of kaolin powder that was distinguished with the stearic acid modified kaolin nanoparticles. As it is shown in the figure attached, kaolin powder generates broadly a hexagonal morphology, stacking in abundance of neat and wedge-shaped pores, indicating the hydrophilic nature of kaolin powder. As the kaolin powder was modified with the stearic acid, the layer of stacking hexagonal forms and plated crystal shape covers the stacking of kaolin shape. This FESM image proved the kaolin nanoparticles have been successfully modified by stearic acid due to the difference in surface morphology of pristine kaolin and stearic acid modified kaolin nanoparticles. On the right side, as it is shown, greater concentration show better uniformity of the layer of substrate. Distribution of stearic acid modified kaolin nanoparticles well uniform in concentration 20% than other concentration. With higher concentration, more molecules present in the solution, more areas on the superhydrophobic surface are exposed to the nanoparticles. When droplets fall on the surface, it remains on the surface and becomes hydrophobic because lower air gaps between the molecules prevent the droplets penetrating into the gaps. Therefore, FESM images show that the dispersion of the stearic acid modified kaolin nanoparticles become more uniform as the concentration of the particles increase. The next result displayed is surface roughness analysis via atomic force microscopy (AFM). Surface roughness is one of the significant parameters in creating hydrophobic surface. When surfaces are rougher, they become more hydrophobic and water droplets on top tend to become almost spherical. The surface roughness of the pristine membrane made of silicones was distinguished with the surface roughness of the stearic acid modified kaolin films with different concentration of stearic acid kaolin modified nanoparticles. Based on the result presented above, pristine membrane without stearic acid kaolin modified has the smallest value of roughness, which is 1.878 nanometer, only among all the measured samples. The presence of silicon in the membrane increased hydrophobicity but reduced the roughness. On the other hand, the value of roughness increased as the modification of the pristine membrane by the stearic acid kaolin modified kaolin nanoparticles occurs. The result above displays when the concentration of stearic acid kaolin modified increased, the value of surface roughness also increased. Therefore, surface roughness of the stearic acid kaolin modified silicon rubber film is greater than the pristine membrane. The self-cleaning performance was stated on the samples as one of the significant applications of the hydrophobic surface. In the experiment, the self-cleaning effectiveness was evaluated by distributing the contaminant particle, which is graphite powder, over the membrane and determining how easily rolling droplets could move the particle away. Based on the result, pristine membrane shows self-cleaning performance as the membrane made of silicone, which is inherently hydrophobic. The self-cleaning performance of all stearic acid kaolin modified silicone film display similar outcomes. It shows that the film have better self-cleaning performance than the pristine membrane. In conclusion, the prepared silicone rubber film present broad and hierarchical hydrophobic alkyl chains that are covalently bonded. Consequently, the surface shows hydrophobicity with the higher contact angle of 113.9 degrees. The silicone rubber film is successfully fabricated via stearic acid kaolin modified kaolin nanoparticles. As a result, the stearic acid modified kaolin nanoparticles silicone rubber film show excellent self-cleaning performance when repeated for more than 30 times. This method provides an efficient, cost-effective, and environmentally friendly process to improve self-cleaning performance, and it is profitable for further studies. That's all from me. Thank you.